Today we'll cover phase equilibrium. Consider these two containers. One contains only steam and the other is half filled with water and the rest is steam. And we apply some heat to increase the temperature, and let's predict the temperature of the systems. As you well know, the temperature and the pressure of the first system will increase and increase and increase if we continue to apply the heat until the temperature is equal to the flame temperature, right? But for the second case, the half filled, which is half filled with water, the temperature and the pressure will increase, but the rate of increase is not that high compared with the first case. So this is the typical phenomenon when we have a two phase within a system. When there is a phase change, the temperature seems to change slower. Sometimes it seems to stand still. And in our daily life, we often boil the water. Even though we continue to apply the heat, the water temperatures stand still at 100 Celsius because of the phase change. So, for example, two-phase system does not change in temperature in spite of large heat input, and the heat input is used for phase change. So, and we call here is the list of heat of phase change. Heat of vaporization means the heat used for vaporized liquid. Heat of liquefaction is the heat output when we condense the vapor into liquid. And the same for the heat of solidification and heat of melting and heat of sublimation from solid to vapor or from vapor to solid. Now we consider two systems again, but the composition of their system is a little different from the previous case. In the first system, we have only water, and for the second system, we mixed ethanol with water. So in the second system, we have a mixture of water and ethanol. Then we start heating two systems. And can you predict the temperature and pressure of these two systems? You may well know about this kind of system. The water temperature will increase and increase. But when it reaches 100 Celsius, the temperature change is not that high because the heat is used for change the phase. But for the second case, what happens? What happens to the second case? Temperature will increase and increase. And when the temperature is equal to the boiling point of ethanol, then the ethanol starts to boil, and the temperature will increase and increase again. And when it reaches 100 Celsius, the water starts to boil. Let's summarize the phenomena again. The single component system, the first system, boils at 100 Celsius if we keep the pressure at 1 bar absolute. But the two component system, the second system starts to boil at 775 Celsius, and the temperature will increase again and again. And when you reach 100 Celsius, the temperature increase stops and the water starts to boil. So this kind of so for the second system, if we measure the temperature of the system, it looks like this. Time, x-axis is time, the y-axis is temperature. When it reaches 75, the boiling point of ethanol, the lighter component, we call it lighter component, the component that has lower boiling point. The ethanol started to boil, but the temperature still increase like this. When it reaches 100 Celsius, the temperature stands still, even though we continue to apply the heat. When all the water is vaporized, the temperature will go down. Okay, this is the expected temperature profile for the second case. But consider this case, a mixture of methanol and water, not ethanol. As you know, methanol is not miscible with water, right? What I mean is when we put ethanol and water in a jar, the bottom is water. The bottom part is water. The upper part is methanol. And the methanol and the water is not miscible. So in this case, for the second case, a mixture of methanol and water, the temperature profile is like this. At this temperature, at the boiling point of methanol, all the methanol boils up. Then we only have water, and the temperature will increase. Then water starts to boil. What's the difference between the mixture of ethanol and water and the mixture of methanol and water? Consider this region. Okay. At this, in this intermediate temperature range, the composition of the composition from the first case is a mixture of ethanol and water. And if we check the vapor composition, maybe half of the vapor is ethanol and the rest is water. But for the immiscible case, the mixture of methanol and water, the majority, maybe 99.9% is just methanol. So this is the meaning of a miscible mixture. When we say miscible, it means miscible in molecular scale. And we can mix the two substances in various scale. And if we make a small particle, like a small droplet, it looks like as if they are mixed. But from the thermodynamic scale, when we say they are miscible, they should be mixed in a molecular scale. Okay? So ethanol and water mixed in molecular scale, but the second case, a mixture of methanol and water, does not mix in a molecular scale. So they shows as if they are two-phase. Actually, they are two-phase. Okay? For the second case, we have two-phase. The lower phase is water, the upper phase is methanol. For the first case, ethanol and water are completely mixed in a molecular scale. So consider the first case, the completely mixable case. Water is mixed with ethanol in a molecular scale, and here we have water and ethanol mixture. We apply some heat, then some vapor will be generated from the mixture. And the vapor is condensed by cooling water, then we can get some liquid in the beaker. So guess the composition of the vapor and composition of the liquid in the beaker just after the boiling point, near the 75 Celsius, and close to the end of the boiling, and near the 100 Celsius. So the answer is just after the boiling point, close to 75 Celsius, the majority of the methanol of the vapor would be ethanol. Okay, there will be some roughly speaking, 99% is ethanol, and 1% would be water. And when the temperature is close to 100 Celsius, the majority is water, and we may have 1 or 2% of ethanol. But in the middle between the 75 and 100 Celsius, for example, around 90 Celsius, the composition of the vapor would be 50-50. 50% would be water, and 50% would be ethanol. Any question? Here is the general pictures of multi-component phase diagram. as you saw in the previous example, boiling temperature depends on composition. And here the liquid is still boiling. And the mixture of ethanol and water boils in this range, and from 75 to 100 Celsius. And you may know that the boiling point depends on pressure. I will explain again. And the composition of vapor depends on composition of liquid and pressure and temperature. Heat of phase change and heat of vaporization or heat of melting also depends on composition, pressure, and temperature. I will explain one by one in the following figure. This diagram is called phase diagram. This diagram shows the phase in terms of pressure and temperature. Look at the x-axis. X-axis is temperature, and y-axis is pressure. Usually x-axis is shown in linear scale, and the y-axis is shown in logarithmic scale. When temperature is low and pressure is high, we have solid. When pressure is low, temperature high, we have a vapor. And only in the intermediate pressure and temperature, we have liquid. There are 2 points here. One is a triple point, the other is a critical point. Triple point is the pressure and temperature where three phases coexist, and we can observe solid, liquid, and vapor all together at the point. As it means, it's a point. Okay? So it's very hard to observe that point experimentally. The other point is very important, critical point. Critical point means pressure and temperature above which liquid and vapor are indistinguishable from each other. So above the critical point, we cannot get liquid phase. Okay? We have air here. Take a look at this lighter. It contains what? What is in this lighter? It is called butane. Commercially, we call it butane LPG. It's liquefied petroleum gas. If we release the gas in the atmosphere, it vaporizes. In other words, we have LPG here, and if we compress the LPG, if we increase the pressure of the LPG, we can get liquid. Okay? What happens to air if we increase the pressure? We have air here. If we increase the pressure of this air, do you think we can get a liquid? No, actually no. Why? The temperature, the ambient temperature, is higher than the critical temperature. For air, the ambient temperature is around here. Okay? It's ambient temperature. The ambient temperature is greater than the critical temperature. That means above the critical temperature, we cannot get liquid by compression. How matter large it is, the magnitude of pressure is not important. That at any pressure, we cannot get a liquid. So critical temperature and pressure is very important for liquefaction. The most gases, the most light gases like oxygen, nitrogen, and hydrogen, that kind of gases cannot be liquefied by compression. LPG is okay. That means the ambient temperature for LPG is around here. Okay, the ambient temperature for LPG is here. So the ambient pressure is around here. So LPG is gas. I don't know why it's not working. So the LPG is here. If we increase the pressure, in other words, if we raise the pressure, we can get liquid here at this pressure. LPG is here. If we increase the pressure of LPG or if we compress the LPG, we can get liquid here. So the pressure of this lighter is here. Okay? Can you understand? Saturated liquid or vapor line means this line. Okay? This line, along this line is a boundary between liquid and vapor. On this line, we can observe liquid and vapor together. This is the saturated liquid line for water. Okay, note that the y-axis is shown in millibar. So 1,000 millibar is 1 bar. At 1 bar, the boiling point is 100 Celsius. If we reduce the pressure, in this case to 0.6 bar, the boiling point would be 85 Celsius. That's why we have half-cooked rice if we cook the rice in mountain areas. Okay, in mountain areas, the pressure is a little lower than 1 atm. So the boiling point of water is slightly lower than 100 Celsius. So the phase of a substance in our daily life is closely related with the relative position of triple and critical point to the atmospheric pressure and temperature. This phase diagram is for water, and the triple point for water is close to 1 Celsius and 1 bar in absolute case. So our daily life is within 0 Celsius to 100. So in this region, the pressure is usually 1 bar in our daily life. So we can observe gas and liquid. if the temperature is lower than the critical point, the temperature is lower than 0 Celsius, we can observe solid and vapor. This phase diagram for CO2, carbon dioxide. The triple point is here. The triple point is around -60 Celsius, and the triple point pressure is around 5 bar absolute. Our daily life is around 10 to 40 bar. 10 to 40 Celsius, and the pressure is 1 bar. In this area, what we can observe is for CO2 is just the gas, gaseous CO2. At 1 bar, following the 1 bar line, we can decrease the temperature. Then we have solid, not liquid. So we can observe the solid CO2. That is called, what is the name of solid CO2? Yeah, dry ice. We have dry ice. Surprisingly enough, the temperature of solid CO2, dry ice, is -80 Celsius. Can you believe that? You may have experienced that you have the dry ice on your hand, but does it did you feel that cold -80 Celsius? If you hold ice, water ice, at -10 Celsius, you can feel it is very cold. But dry ice is not that cold. Why? For the water ice, it melts, and the part of the ice becomes water, and we have wetting surface between the water, between the ice and our skin. So effective heat transfer is very active because of the melted water. But for the dry ice, we have some vapor from the dry ice. So the gaseous CO2, gas itself is a good insulation material. So we cannot feel that cold when we touch the dry ice. Anyway, if you wanted to get liquid CO2, what should we do? We are here, and we are at 20 Celsius, and the pressure is 1 bar. And in order to get the liquid CO2, what we should do is to just increase the pressure. If we increase the pressure around 40 bar, 40 to 60 bar, we can get liquid CO2. So that's the problem for carbon capture and storage problem. Okay? In order to transport CO2 in liquefied form, we should increase the pressure to 40 to 60 bar. Okay? Anyway, in summary, the phase of a substance in daily life is closely related with the relative position of triple point and the critical point. relative to the atmospheric pressure and temperature. Okay? Next term is normal melting point and normal boiling point. Here, the word normal means atmospheric pressure. Assume that we have solid at 1 bar and at the low temperature, and we increase the temperature of the solid, then the solid will melt at some point, and the temperature, the point, is called normal melting point. For water, it is 0 Celsius. We apply we continue to apply the heat, then we can get 100% of liquid. If we further increase the temperature of the liquid starts to boil when the temperature is 100 Celsius. That point is called normal boiling point. That means if we increase the pressure or decrease the pressure, the melting point and the boiling point will change. Typically, the saturated liquid solid line, I mean this line is a little vertical. I mean that it's not sensitive with the pressure. So even though we increase the pressure, the melting point of ice is close to 0 Celsius. But the saturated liquid vapor line, we usually boiling point line, is very sensitive to pressure. As I explained previously, the y-axis is linear and x-axis is linear, and the temperature scale is in linear, and the pressure scale is logarithmic. Look at this. Look at this phase diagram for CO2. This axis, the temperature scale is linear, and the pressure scale is logarithmic. I mean the 1 bar, 10 bar, 100, 1000. Okay, so the small change in pressure can result in a large change in boiling point. You may know this diagram. I excerpt this paragraph from Wiki. Let me read the paragraph. The Vitruvian. The Vitruvian man is a world-renowned drawing created by Leonardo da Vinci around the year 1487. It is accompanied by notes based on the work of the famed architect Vitruvius Polier. Maybe he was Roman or Greek? Roman? And anyway, I mean the original work was done by Vitruvius Polier. The drawing, which is in pen and ink on paper, depicts a male figure in two superimposed positions with his arms and legs apart, simultaneously inscribed in a circle and a square. The drawing and text are sometimes called the canon of proportions, or less often proportions of man. I can understand the meaning of canon, but I can understand the meaning of proportions of man. Okay? So, this is the circle and this is the scale. Okay? One point we can learn from this diagram is that if we stretch our arms to outside, the length is equal to our height, right? And this kind of proportion is applicable to all mankind. Not all, maybe 99% of mankind. You agree? And the stretch of your arm is equal to your height? No? Okay, let's test it. You can stretch your hand from the bottom to here. Okay. Can you measure this with your arm? 팔을 쭉 뻗어서 아래 위로 딱 대고 그래. 아니 이렇게 뻗어서 이렇게 이렇게 아니 이렇게 딱 되면은 이거 같아? 같지? 야. Exceptionally, someone has a longer arms than their height, but this proportion, I think, is applicable to 99% of the mankind. So this picture is called proportions of man. The reason why I show this diagram is to explain about the principles of corresponding state. The question that has risen to the thermodynamic engineer is that is there any ratio for substance like that of a human? I mean the ratio like the proportions of man. That is the principles of corresponding state. So the idea is very simple. We normalize the actual properties by the critical properties. So the base, denominator is the critical properties. So we call their divided, that the scaled properties is called reduced property. So the reduced pressure PR is just the ratio of actual pressure divided by critical pressure. Reduced temperature is actual temperature divided by critical temperature. Reduced volume is the ratio of actual volume to the critical volume. Here volume means that the reciprocal of density, the volume per 1 kilogram or volume per 1 mole. This diagram shows the power of principle of corresponding state. The x-axis is reduced volume. Y-axis is reduced pressure. And we plot the experimental data. The first line is the the line on the right hand side is the saturated liquid, the line on the right hand side is saturated vapor and superheated vapor. Forget about the superheated vapor, just consider saturated vapor. If we plot the experimental measurement, we can measure the reduced volume and reduced pressure, and we can plot on this diagram. And the empty circles of methane and the solid circles for nitrogen. Even though they are different substances, the measurement fall on a line. And this is kind of the proportions of materials. Most of the material will follow this behavior, but unlike maybe 99% of the mankind will follow the proportions of man, but for the materials, for the pure substance, this kind of principle does not hold. That this kind of the principles of corresponding state is applicable to light gas, like light and non-polar molecules like nitrogen, hydrogen, helium, methane, ethane. If we consider water, the water shows a big deviation from this kind of this line. So the one important task of thermodynamic engineer is to estimate the deviation. Okay. Anyway, the backbone of physical property estimation is based on these principles of corresponding state. This is the starting point. And we, the thermodynamic engineers, try to find the gap and the deviation from the principles of corresponding state. Let's consider the vapor composition from a liquid mixture. We have a multi-component mixture. As temperature goes up, we warm up the liquid, and then we can observe 5 states. First is subcooled liquid. Second, the bubble point. The next is the bubble point to dew point. Dew point, superheated vapor. So I will explain one by one. Subcooled liquid has no vapor. That it has vapor because it has temperature, but vapor generation from the liquid is not active. So subcooled liquid has vapor, but the vapor generation from liquid is not that active. At the bubble point is the temperature at which a small drop of vapor is formed, and it's the first, the lowest temperature the liquid starts to boil. As you expect, the main component of the vapor would be the lightest component. And the bubble point to dew point. Now, as we saw in the previous example, the liquid boils in this range from the bubble point to dew point. In the middle temperature, the bubble point to dew point, a large number of bubbles are formed, and the composition of a vapor is a little like that of liquid. As the temperature close to dew point, the majority of liquid has already vaporized. So dew point is by definition is the temperature at which the last drop vaporizes, and it mainly consists of the heaviest component. Then if we increase the temperature of the vapor, we can get superheated vapor. So what I want here is that you should understand the meaning of subcooled, bubble point, dew point, superheated. I will explain again in this diagram. This diagram is for the LNG, liquefied natural gas. Let's start from minus 200. Minus 200, the liquid, the LNG is subcooled liquid. It had some vapor above the liquid phase, but the temperature of liquid is far less than the boiling point. As we increase the LNG temperature, then we can observe a bubble, a small bubble. This point is called bubble point, and the first drop of a bubble is formed at this temperature. If we increase the temperature, the LNG will boil. Okay, and around minus 100. Okay, the composition of vapor may be close to composition of LNG. At the dew point, now we have a small drop of liquid, the last drop. So by definition, the dew point is the temperature at which the last drop of liquid vaporizes. So why it is called a dew point? If we reverse the direction, that if we start from superheated vapor, and if we decrease the temperature, at this dew point we can observe the first liquid drop. That is dew in Korean isul. So that's why it is called a dew point. So the boiling point range for LNG at this pressure, maybe 10 bar, is between minus 30 to around minus 30, minus 130 to minus 30. The range of boiling is about 100 Celsius. So this is the contrasting point. The pure component boils at one point for a given pressure, but the multi-component mixture boils in a range of temperature. At this example, the range is around 100 Celsius. Any question? The subject from now on is about the degrees of freedom. The first question is, how many conditions should be fixed to get the saturated pressure of pure water? And we want to know the saturated pressure of water. Then what should we know? As you see, they're saturated in their phase diagram. If we know the temperature, we know the vapor pressure from the liquid vapor saturated line. So if we know temperature, if the temperature is fixed, we know the pressure. So degree of freedom is 1. If we know the temperature, we can define the pressure, the saturated pressure. The second question is, how many conditions should be fixed to know the enthalpy of a steam? Okay? In this case, the steam is superheated vapor. We wanted to know the enthalpy of the steam. From your thermodynamic knowledge, I'm sure you know that the enthalpy is a function of temperature and pressure. So we should know two variables, in this case pressure and temperature. The next question is a kind of general question. How many conditions should be fixed to know the enthalpy of a boiled gas from 5-component LNG? The liquid contains 5 components, and we wanted to know the enthalpy of the boiled gas from the 5-component LNG. This kind of question can be answered by the degrees of freedom. So this some thermodynamic scientists studied this problem for us, and this rule is named Gibbs phase rule. I'm sure that you know this famous thermodynamic scientist. So the rule is F is equal to 2 plus m minus p. F is the degrees of freedom, m is the number of components, and p is the number of phase. That is, if you know the number of phase, number of components, then you can define the degrees of freedom. That means, in order to define the system, you should the variables, and the number of variables is equal to the degrees of freedom. Let me show you an example. In the previous example, we have 5 components in the LNG. So the number of components is 5, and the number of phase is 2, LNG and vapor, a boiled gas. So we have 2 phases. So the answer is 5. Degrees of freedom is 5. So if you fix 5 variables, you can define the system, and you can know the thermodynamic properties of the system. You can know the composition of the boiled gas. You can know the composition of the LNG. So 5. If the 5 variables are independent from each other, any set is okay. First set is PT and mole fraction over 3 components. Then we have defined 5 variables, PT and 3 components in the liquid. So we specified 5 variables. So then from set 1, we can define the system. Define means we know all the thermodynamic properties of the system. Set 2, mole fraction of 4 components in liquid and temperature. Then 5. How about the mole fraction of 5 components? As you know, the the summation of mole fraction should be equal to 1. So last mole fraction is dependent on the previous four fractions. So if you construct the S3 mole fraction of 5 components, you need still one more variables to be defined, because the last one is dependent. Any question? Solution for multi-component liquid vapor equilibrium. I think you have similar experience in your high school ages. So in this case, we have a liquid, and the mole fraction of the liquid is x1, x2, blah blah blah, xn. They are n component. The mole fraction in the vapor phase is y1, y2, blah blah, yn. We have a system pressure P here. Then we can construct equation for pressure, temperature, and partial pressure of I component is equal to yi times P total for I to m minus 1. As I told you, the last equation is dependent, and the Pi, the partial pressure of I, is equal to xy times P vapor pressure IT. What is the meaning of this equation? For pure component, the pressure of I component is equal to the vapor pressure at the temperature. When the liquid composition is not 1, the mole fraction of liquid is reduced from 1 to x1, then the partial pressure should be proportional to xy. Maybe you may remember the law, Henry's law. Is the first time you ever heard? No. So what I wanted to emphasize is that it's the kind of mathematics. Okay, we can construct this relation, and we solve this equation. Then we can estimate y1, y2, blah blah, y, x blah blah, xn. It's that so what I want to show is that if you want to know why the mole fraction in the vapor and mole fraction in the liquid phase, you need to construct this kind of equation. But the Henry's law and the Raoult law is just kind of approximation. And this kind of this is the ideal gas law. And the partial pressure of component 1 is equal to mole fraction of y times total pressure. This kind of equation holds only for ideal gas. In real world, the commercial coals like HYSYS, Aspen solve this kind of problem. So you don't worry about how to construct this kind of equation. So what is important for you is to to know the background, the thermodynamic background, or to understand the degree of freedom, understand the superheated vapor, subcooled liquid, and liquid vapor equilibrium. Actually, the fundamental equation is the Figesty relation. The liquid phase Figesty should be equal to the gas phase Figesty. I guess you may have not heard about Figesty. It's another expression for pressure. Okay? In this equation, we correlate why the mole fraction in vapor pressure and in the liquid pressure through the partial pressure. But for liquid vapor equilibrium, what should be equal between liquid and vapor phase is Figesty, not the partial pressure. So I think it's too much for you. And what is important is that Figesty is the important property in the liquid vapor equilibrium. But when you use commercial codes, commercial process simulator, it's not that difficult. The program itself check the degrees of freedom, so it prevents from you overspecifying the problem. Okay.